for having me. I'm Henry, and I'm the developer of MOPs, the motion graphics toolkit for Houdini. If you haven't heard of MOPs before, it's short for motion operators, and it was a toolkit originally designed by myself and Moritz Schwind from Tagma way back in 2018. The goal was to give Houdini better tools to accomplish typical motion graphics animations, similar to Maya's MASH or Cinema 4D's MoGraph toolkit. These tools allow you to create animations like this with just 1 or 2 keyframes rather than having to animate by hand or design your own solver. Since our original debut, it quickly became obvious that there were tons of applications for this kind of toolkit outside of just motion design. MOPs is now a general-purpose toolkit for handling transformations and creating mask attributes, and it's expanded to modeling, volumes, simulations, shading, and rigging. MOPs is now being used across multiple industries, pretty much anywhere you'd find Houdini: feature animation, visual effects, video games, commercials, medical animation, and big tech. Now that I'm done bragging, I want to quickly clarify what MOPs is. It's easy to just think of it as a plugin or an add-on or whatever, but if you've ever looked inside any of the open source MOPs tools, it's all just SOPs, Vex, and Python under the hood. Everything it's doing is effectively native Houdini. What MOPs really is a UX layer on top of Houdini. It's taking all of the complexities of animating lots of things at once and boiling them down into simpler concepts. If you've ever hung out with animators and watched them talk about a shot they were working on or a scene from a movie they really like, you'll probably see them gesturing wildly and making whoosh noises or something like that. They're much less likely to be talking about what slope their keyframe tangents are at or exactly what channels they're setting where. Waving your hands around and saying pew, pew, pew is way more intuitive and way more human than slogging through all the complex math that's involved in animating these objects from the computer's point of view. That's the whole point behind a good user experience. Knowing how your users want to think about a problem and then giving them the tools to go whoosh with a minimum of friction. Let's talk about some of the fundamental concepts that UX designers use in order to reduce that friction. The first one I want to talk about is cognitive load. This basically means the amount of mental resources needed to work with an interface. The more effort that a user has to put in order to understand what a thing's meant to do and how it's meant to be used, the less of that effort is going to be used in actually solving the problem at hand. If you have to stop and think for a second every time you swing a hammer, you're not going to get much carpentry done. For example, if you want to apply Euler rotations to a number of objects at once in vanilla Houdini, you have to convert the vector describing this rotation into a matrix, extract the existing packed transform matrix of each copy, multiply the 2 matrices together in a specific order, depending on whether you want world space or local space rotations, and then set the packed transforms to the result of this multiplication. Conceptually, the desired effect is not that complicated. It's just rotations, but the steps that you have to take to get that effect are not at all intuitive. MOPs transform is just a UX wrapper around all that math. It's providing the shortest possible path between the user's intent, which is conceptually very straightforward, and the result on the screen. Most HDAs are implicitly designed for reducing cognitive load. The inside of an HDA is usually much more complicated than the outside, after all. But there's some more specific things that you can do when making tools that can help a person have to think less while using the tool. The first and most straightforward way is through a good parameter interface. Information hierarchy is a really important concept to keep in mind here. You want to make sure that, just like any simulation you'd run in Houdini, you're working from big to small. The UI should encourage your users to make the broad strokes first before drilling down into the finer details. Most users are used to reading interfaces from the top down and left to right, so moving more important groups of parameters towards the top and using tabs to group things from left to right, either in the order of importance or the order of consideration in using the tool, can make a big difference in overall readability. For example, here's the parameter interface for MOPs Greeble. It's a recursive subdivider. Up at the top are the most important choices. How many subdivision iterations do you want to run? Where do you want to cut edges? What's the fall-off attribute? All that stuff. Then the optional things show up. What edges do you want to cut first? Do you want to run extrusions and all that? After those optional choices, you have a list of tabs providing more choices, followed by the tab for cleanup operations, and then the last tab for optional output attributes. The assumption is that the user is going to dial in their overall look first and then consider cleanup operations, how to polish it, and then decide what attributes they may or may not want to keep around at the end of the operation. One of the best ways that you can reduce cognitive load with HDAs is, unfortunately for all you tool developers, creating interactive handles. Python states, like any GUI program, require a lot of boilerplate code, and they're often really tedious to write, but the time that you put into them up front can save way more artist time down the road. Some things like simple transform handles are built in, and you can simply promote them to your HDA, but for anything beyond the built-in handles, you have to get dirty with Python. For example, a cool thing that you can do in Solaris is push objects around and have them collide with each other, just like with a typical transform handle. MOPs physics edit, which is a SOP tool, does something similar by using Python states to run a quasi-static bullet solver in the background while the user's interacting with the handle, and then it stashes the result upon exiting the tool state. Python states allow you to choose exactly how a user makes a selection, where the resulting handle is drawn, what parameters are updated when the user manipulates the handle, and what happens inside the HDA during all of those things. There's a lot that's going on inside the tool, but the interactive handle is what ties everything together and makes all of these complicated steps feel like you're just playing with toy blocks. I don't have enough time to really dive deep into the guts of Python states in this presentation, but if you want to dig in, Paul Ambrosison, who's coincidentally presenting after me, has a really great tutorial that explains how to leverage them to create better GUIs for your tools. GUI program is going to be a slog no matter what you do, but having this skill in your back pocket can mean the difference between a tool artists won't touch and a tool they'll actually enjoy using. Next up is Hicks Law. A user's decision time increases with the number and complexity of choices. This one's a real doozy in Houdini. It's one of the major reasons why Houdini can be overwhelming for so many new users. Just look at the sheer number of tools that you have to sort through, and that's before you even get to any of the parameter interfaces. The more stuff that you throw at a user at once, especially if there's no clear information hierarchy, the harder it's going to be for them to make quick decisions and find the tools or the settings that they're actually looking for. You can mitigate this in tools by ensuring that the user only sees what they need to see at any given time. Let them figure out the broad strokes first and then dive into the more nitpicky stuff when they're ready. For example, MOPs Randomize just has a tiny set of options up front, essentially asking you the most important question first: what do you want to randomize? It isn't until you start selecting things that you start seeing more options pop up, like minimum maximum ranges, additional hidden options for probability distribution, things that are used more rarely and don't need to be shown right away. Making good use of roll downs, tabs, and the hide when and disable when options in your HDA interface can end up saving many hours of artist time over the course of a show, even for people who are already comfortable with Houdini or familiar with your toolkit. The last basic UX concept I want to talk about here is called Jacob's Law. Users want your interface to work according to patterns that they already know. If you introduce someone to a tool or an interface that doesn't look or behave like anything they've ever seen before, they're going to have to waste a lot of time and mental effort wrapping their head around how your tool is meant to work. If you've ever seen Demolition Man, the 3 seashells is a perfect example of Jacob's Law in action. It's the most memorable gag in the whole film. To this day, no one can agree on how one would use the 3 seashells. MOPs is a pretty straightforward example of Jacob's Law here because the central idea of transforming lots of things at once, modulated by some kind of field, was already long established in MASH for Maya or MoGraph in Cinema 4D. Anyone who's already familiar with either of those tools is going to be able to pick up the basic concept pretty quickly. At a deeper level, though, MOPs is also trying to be as Houdini-like as possible in how it utilizes attributes and standard patterns in Houdini. Attributes like name, ID, rests, and all that are generally well understood by Houdini users, and MOPs uses those built-in design patterns whenever they're applicable. There's no reason to reinvent the wheel with your tools unless doing so is going to end up saving time and effort with the end user. Outside of these basic rules of UX, I wanted to get a little bit more Houdini specific next and talk about the balance between usability and versatility when building tools in Houdini. The old model of tool development in Houdini, like most things in its history, stemmed from the needs of large VFX houses. The assumption was that Houdini would give users all the nuts and bolts you needed to do anything you could think of, and the genius TD nerds at those big shops would use those atomic nodes to build higher level tools and then distribute them to the artists for shot work. As Houdini started to branch out into indie-sized studios and motion graphics houses, though, this assumption that an in-house TD would solve all these usability problems no longer holds. Generalists working in shorter timeframes with less resources can't always wait for their hero nerd to swoop in and write a tool for them. Side Effects responded to this need in part by releasing more high-level tools of their own. Think about all the new SOP-wrapped simulation tools like the Vellum Solver, PyroSolver SOP, or the Flip Solver SOP. Under the hood, they're using the same atomic nodes as before, but now they're wrapped up as convenient tools with built-in forces, visualizers, and options for otherwise difficult problems like guided destruction. The key concept to take from this is that the low-level framework is developed first, followed by wrapped-up convenience tools that utilize that framework to solve a problem. Your user still has access to all of the atomic nodes if they're clever and dedicated enough to use them, but they also don't have to reinvent the wheel every time they build a setup for a typical effect. You can author USDs using low-level LOPS nodes, or you can use a component builder and have a way easier time for 90% of your assets. MOPs as a toolkit is developed the same way. You have a few core nodes for handling transformations, like apply attributes and extract attributes, And the rest of the tools are just setting up interfaces and attributes to be fed into those core tools. This serves two important purposes. First, it satisfies the basic programming principle of don't repeat yourself. And second, it gives your end user the ability to solve a problem in multiple ways, either using the high-level tools or the low-level tools to solve edge cases. Dive targets and expressions are also great ways to add to the versatility of a node. Think about how you can dive into the Vellum solver to add custom forces or use expressions to modify Vellum constraints per primitive. Adding that extra flexibility lets expert users get exactly what they want without forcing them to unlock and modify your HDA, which should be an absolute last resort. Another important point to make while building tools, especially in the context of a larger toolkit, is to try to avoid creating single-purpose tools. What I mean by single purpose are HDAs that can only solve a specific problem in a specific way. The more particular that your inputs and outputs need to be for a given tool, the more tools that you're going to end up needing to create. It's a bit like having a kitchen full of gadgets that can only do one thing. Your drawers are going to get clogged up with tools that are useless for 90% of applications when most of the time what you really need is a chef's knife. It's Hicks Law in action. This is real, by the way. I didn't make this up. You can get this on Amazon. MOPs is designed to have nodes be as versatile as possible in order to keep the number of operators that you have to memorize at a minimum. Fall-off nodes, for example, are just setting float attributes on geometry. By default, they're designed to act as weights for MOPs modifier nodes, but they can be used to modulate pretty much anything from shaders to Vellum simulations to any SOPs that accept a scale by attribute. Modifiers will apply their same effect to either pack transforms or to standard template point attributes. Allowing room for tools to be used in unexpected ways gives your users more chances to get creative. The last point that I wanted to make regarding this balance is that artist time is almost always more expensive than CPU time. When you build tools that are simultaneously easy to use, flexible, adaptable to edge cases, it's inevitably going to slow your network down a bit. You're making the computer work a bit harder in a lot of cases to make up for these edge cases. So you're going to frequently run into situations where your amazing tool doesn't work as quickly as a few bare bones lines of VEX. But as long as the tool is still reasonably responsive to artist input, my position is that you shouldn't sweat it too much if you lose a few milliseconds here and there. Optimization is still an important step for any tool, but you shouldn't sacrifice usability for it because artist time is at a premium. Before I get to the last section, I just want to quickly talk about a few other important things that I've learned from accidentally becoming a tools developer. I didn't go to school for programming or for anything related to UX at all, so some of this might seem obvious to people who are more dedicated to it, but here's some last-minute advice for you. The first one is unit testing. You absolutely must unit test. Sorry. It doesn't have to be terribly complicated or fancy a setup, but you have to establish a consistent series of tests that you can run every time that you're ready to release a new update of your tool so that you can be 100% certain that you didn't break something with your latest update. Early on in MOPs development, and honestly, sometimes still, I would just quickly release new versions with bug fixes that introduced new bugs down the line, and then sometimes I'd end up breaking things back and forth for several experimental releases before I actually nailed down the root of the problem. Learn from my mistakes, unit test. My unit test here is pretty simple, but it works. It's a bunch of different SOP operations that are either compared directly to each other or is some cached known state that is considered good. I cache that to disk and then run the results through a shape diff SOP. If any of the point positions are non-zero, I know that my transform operations aren't doing what I think they're supposed to be doing, and so then I can just throw an error. I then chain all those SOP nets up into a top net, and I can cook them all in a row, and if anything comes up red, I know I screwed up. Any tool that you build should be similarly testable and validated anytime you release. This also might seem obvious, but it's really important to use HDA versioning to protect your users whenever you can. And by protecting users, I mean allowing them to keep their older scenes from breaking when they update to newer versions of your toolkit. If you add a version suffix to your HDA and change that suffix every time you update something big, like the name of a parameter or just overall parameters in general, you can prevent unexpected changes to people's scenes when they update. And finally, it's really important to get to know your users. It can be really difficult to get good feedback on tools that you've built, especially if you're not building them for a facility that you work at. Find people that will give you feedback and watch them use your interfaces. One of the most useful kinds of feedback I get from users is watching them record live streamed MOPs tutorials or just watching them work with MOPs when they're using it to build whatever. and just sort of watch them struggle with whatever particular parts of the interface, or watching them miss what I'd thought were obvious tools or settings that would have solved their problem in seconds. It's the most useful hard data that I could get on how intuitive and effective the interfaces were. Try to get data from a broad range of users, both novice and experts, because they're all going to teach you something different about how your interface is being interpreted. Okay, now the fun part. I've been talking nothing but theory this whole time, and that's boring, so I'm going to end with a practical example. I'm going to give you a tour of the insides of one of the proprietary tools. This is MOP's Typography. So the goal of this node is to make it easy to create clean extruded type from fonts or from vector files. Conceptually, this is really simple stuff, but the reality of what has to happen under the hood in order to make this feel natural is way uglier. So let's dive in. Let's do a quick overview of MOP's typography just so you have some context for what's happening inside. Start that. So this tool generates extruded and or beveled geometry from either font files or from curves that can be created either in Houdini or imported from Illustrator or any other vector format. It supports word wrapping, justification, and alignment, similar to other text box tools that you'd see. The output letter forms are generated as packed primitives with their pivots at the baseline so that they can be animated in predictable ways. The output can be grouped by letter, by word, or by line. You can also quickly adjust the transforms of individual letters using the kerning mode, so it's just a special transform handle. As an added bonus, there's a font browser UI that allows you to quickly filter and search for exactly what typeface you want and kind of dial that look in quickly. Okay, starting from the beginning. In order to support that grouping by word and the word wrapping that's there, there's a bunch of prep work that has to be done. MOPs generates each word by itself in a for each loop so that the word wrapping can actually function. The line height and the space width of the original font are measured and stored as detail attributes by measuring the distance between period characters horizontally and vertically. And then the words themselves are split up and stored as array attributes. Next, the for each loop generates the words one by one. After each word is generated, it's placed next to the previous word by adding the space width we measured earlier to the maximum bounds in X. If the new maximum bounds go outside the word wrapping boundary that we set, or if a line break is detected, the words drop down to the next line using the line height we computed earlier, and then we keep working from there. The indexing attributes for word and line are also added to this loop so that we can group them later. In this second loop down here, each line is justified by comparing its bounds to the overall bounds of the entire block of text. Now the type outlines get cleaned up prior to extrusion. So a fuse and a facet SOP are used to remove inline points or points that are way too close together because that can cause problems with extrusion and beveling later. The vertex normals are then averaged per letter and then compared to positive Z. So if they're flipped, the letter is reversed in order to ensure that the surfaces and extrusions are consistent because some typefaces have backwards Bezier outlines. They're not all made particularly clean. So it's important to make sure that no surfaces are flipped on individual letters. Next up is extrusion. So this is pretty straightforward. Use the whole SOP to open up any holes in the outlines and then extrude and bevel, whatever. But then there's the chisel mode, which is a lot trickier. For that, the holes are filled back in temporarily, and then polyexpand 2D is used to push the outlines inward to fill the interior with edge loops. It's a little bit like creating an SDF of a typeface. This outputs an edge distance attribute that you can then map to a ramp and then use that ramp to push the points outwards based on the distance from the edge. That creates your chisel profile. The peaks of the chisels then get fused or filled depending on user settings. The next step is packing and sorting the letters. So if we generated these letters ourselves, it's really easy because we already have all the attributes we need to do this from the font SOP itself. But if the text is imported from Illustrator, you have a problem. How do you know what's an individual letter? If you just separate by shells the normal way, any dots or diacritics or any other special disjointed characters are going to register as separate transforms. They won't move with the letter itself. Instead, what we end up doing is using k-means clustering based on a specific attribute. By default, this is the Y position of each character, and then a user-supplied line count. So we say that we have 2 lines. This allows for each line to be grouped individually. And then for each line, we flatten all the packed points in Y and then use the fuse SOP to create an attribute for points that are very close to each other horizontally without actually fusing the points. We can then use this attribute to pack any matching points as the same primitive so that a lowercase I will register as a single primitive. Once everything's packed and sorted, we have to establish baselines. When you're scaling or otherwise transforming fonts, the expectation for any type designer is that the transformation is going to pivot around the baseline of the font. And that's the imaginary line that letters sit on. Aside from descenders like the bottom of a lowercase y or q, any letter is going to sort of be sitting directly on the baseline. The baseline is established here by looping over each line and masking out any weird non-ASCII characters, and then figuring out the maximum of the minimum bounds of each letter in y. The highest minimum y bounds in almost all cases, pretty much unless you're doing all caps, is going to be the baseline. Once you know that point, MOP's pivot is then used to set the new pivot point of each packed primitive to fall on that baseline. Finally, we have kerning. This is a bit weird, and it relies very heavily on the Python state handles that I was talking about earlier. Here's how it works. Each transform operation that you do with that handle is recorded as part of a hidden multi-parm block that stores the group mask and the exact transform that's been applied. So the first for each loop in here runs each of those transforms one at a time. But to speed up evaluation while the user is actually using the tool, the Python state stashes and it stashes the current configuration of the letters and then switches over to reading the stash. So while the user is using the handle, it's basically doing destructive edits on a stash that updates itself every time. Each consecutive edit that's driven by the MOP's transform outside the loop is added to that multi-parm block and then written back to the stash for as long as the tool's active. When you exit the tool state, the stash is dumped and we switch back to the evaluated transforms that are coming inside the loop. This is a trick that I stole from the point weld SOP, so if you want to actually see how it works, crack that open and look inside, because that's more or less the same trick. The Python state is what allows the handle to change based on what mode we're in, and it also allows the handle to be placed exactly where we want it. So for example, in the onSelection function, that draws the transform handle at the position of the last selected primitive instead of just averaging in the center of them. It also allows for what's called tracking mode in the kerning tab. With this active, you can just select one letter and then all subsequent letters in the line will be automatically grouped up in that transform operation. So the state handle on selection creates a special group mask expression that includes all points in the same line greater to or equal than that selected primitive's index. And then that is written to the multi-parm group mask. So you can just grab one letter and move everything on that line without having to reposition things individually or select everything at once. And this is all doable via Python states. They're really powerful. One last thing, the font browser that's built into this node. So this is a separate UI that's written in PySide that is a Python library for the UI framework called Qt. PySide ships with Houdini, so it's the best choice for writing custom UIs that don't function within the limits of a standard HDA interface. You can even use PySide to completely replace a parameter interface for a specific type of HDA if you're feeling ambitious, but it does mean that you have to manually link every interaction to getting and setting parameters on the HDA to your interface controls in Qt. In this case, all I'm doing is using this separate GUI window to drive the font parameter on the typography node. So when you select something on this row, it updates the font parameter. This doesn't mean that I got to escape PySide's boilerplate hell entirely, though. For example, this bit of Python that populates the font SOP here is using is using a very hideous regular expression to find a matching Q font object. This is Qt's understanding of what a font is for each font that the font SOP sees. So the problem is that the font SOP displays every variant of a given typeface like Helvetica Bold or Helvetica Italic as an entirely separate font. Qt sees fonts as families that have variants. So the font is Helvetica, and then it has variants, bold, italic, whatever. So this really awful regular expression parses every font that the font SOP lists, and then tries to find a matching Q font, and then applies the necessary modifiers that it finds through that regex, and then adds them to the model view framework for display. When the font browser is opened, the window also stores a reference to the node that created it. So this way, any changes that you make in the UI can be reflected back on the SOP itself instead of just in the separate window by setting parameters via Python. It can also cache the existing node state like the result. So if the user doesn't like what they see, or if they're just scrolling through fonts and decide to make not to make any changes, you can just hit the cancel button instead of having to undo a bunch of times. It'll just naturally restore the node's original state. Being able to quickly narrow down a list of fonts, see a preview, and use the arrow keys to browse through options was by far the most common request that I got for any of the tools that I've built in the MOPs Plus package. And it's pretty obvious why. Like, trying to nail down the right typeface takes a really long time if you have to sit there and click the drop-down menu and then undo every single time you don't like the result. Little interactions like that add up a lot over time. into hours and hours of frustration. So it's really important to streamline interaction patterns like this whenever you have the chance. So there you have it, a conceptually simple node that just makes type on the screen. In reality, an enormous mess of branching paths, edge cases, and scripting cobbled together to make the end user feel like they have control of the situation. It seems like a lot of work to get the right feel, and it is. The whole point of this is to emphasize that getting the raw functionality of a tool up and running isn't enough. Pipeline devs, and I've been one, they all love to laugh at how artists hate working with command line interfaces. They hate working with the pipeline tools that they're given, as if the interface doesn't matter. But the tools that you write are not for pipeline devs. They're for artists. Artists want to work with their hands. Your end user almost definitely doesn't want to sit there and have to learn Bash to use your tool, and they shouldn't have to. A good user experience is going to be time consuming to do well. In most cases, it's honestly harder than writing the tool's functionality itself. But in the end, a tool with a bad user experience will not get used. And that's it. Thanks for listening.
Thank you, Henry. Are there any questions?
Was the typography tool changing the font of an EPS file? Is that what that was?
No, so internally, it either uses the Houdini font SOP to read the Béziers itself, or you can provide it with vectors or curves, depending on how you want to do it. So if you had an Illustrator EPS, you could load it the same way. It's not doing anything that Houdini can't do, it's just streamlining the whole process of reading that stuff.
Okay.
Anyone else? The NASA guy.
Yeah, I was just wondering if you could talk a little bit more about building like a custom like pane using Qt. Does that require a huge amount of background knowledge?
It's the worst. It's hard to give you a basic overview of it, but Qt is kind of its own, it's C++ based. And Qt has this wild thing that they call their model view framework that you can either stay at the surface level and just use prefab widgets for drop downs and things like that, or you can get really dirty with it if you have really complex data. Like for example, I had to use the model view framework in Qt to do the typefaces there, because if I created each widget one at a time as its own text line, it would slow to a crawl. But PySide is basically Python bindings for that C++ library. And so if you use it the way that it wants to be used, which is very particular, you basically get C++ speed out of Python. But as far as giving you a tutorial of it, I would say start by just creating modal dialogues or just creating separate windows that can do things in Houdini. And then if you find yourself enjoying that, which you kind of have to be a masochist to enjoy it, you can eventually use that to replace the parameter interface entirely. So there's a handful of MOPs tools that I didn't show today that you can do a little bit of work in Houdini to essentially flag a node to say, don't use the built-in parameter interface, use mine. And then the Qt window just takes over that section of the parameter interface. So you could build a spreadsheet, for example, and then edit the spreadsheet like you would in Qt using their interface tools and bypass the limitations of Houdini HDAs entirely.
Okay, thanks. Awesome.
So I wanted to ask if the typography node can take in any custom TTF font formats, or is it limited to the library you have?
So you could either use any of the fonts that the font SOP in Houdini would be able to see, or you could path it to your own TTF or OTF as long as Houdini can read it. Generally speaking, you can path directly to font files and use them that way. Or if you just have the vectors defined as an Illustrator EPS or an AI file, you can import that directly. These are all things that Houdini's file SOP can read those same formats. It's no different. This is just a wrapped interface for handling that.
Okay, thank you. By the way, your blog is incredibly helpful.
I'm sorry?
Your blog is incredibly helpful.
Thank you.
Hey, I'm just curious about how do you strike a balance between creating atomized nodes and like more monolithic nodes? Like, do you have a rule of thumb or some advice there?
I don't know that there's necessarily a rule of thumb, but you'll find yourself starting to build lots and lots of tools to solve like a group of problems and just look for patterns of things that you're doing more than once. And it's kind of like a classic programming optimization problem. You start finding yourself using the same function over and over again, or like retyping that same function, wrap it into a function, and then put it in a library somewhere. And HDAs are kind of like functions that you're just like wrapping all of that stuff up into a single thing that you can call.
And do you have like a control group of testers for that kind of stuff, or is it more like of an in-house trial and error?
The in-house is me, so it doesn't work that well. No, there's like a group of pretty dedicated MOPs nerds that of varying skill levels that I know, and so I'll usually, anytime I'm going to release something new, I'll pawn it off to them first, kind of get some feedback on it, get like their overall sense of whether it works or not, and then release it once I know that I'm not making a huge mistake.
Thank you.
I think that's it, Henry.
everybody.
Thank you very much.